we are going to be looking at how to sketch this function f of x equals to 2 over x plus x squared. This problem was proposed to me by a student from the University of Leipzig in Germany. The student goes by the name Songong Kenfak, or you can call her Kenfak. Most students that schooled in the government bilingual high school, Chang, you might know her. So if you are new to this channel, I am Temgun48 presenting this script. Don't forget to subscribe, like and share the video because you're going to learn a lot. And also don't forget to turn on this notification bell so that whenever new uploads are made available, you will not be left out. You'll be the first to be notified. To get to me, you can inbox me using the number on the screen, my WhatsApp number. Now, without wasting much of your time, let's get into business. So the question says, a real value function f is defined on the set of real numbers by this f of x equals to 2 over x plus x squared. It says that we should analyze the function f 5 marks. Whenever you are asked to analyze a function, they're asking you to study that function, okay? Study the function right from its domain and sketch its graph. So let's begin with the domain of definition. The domain of definition, we said, is a set of values of the independent variable x, for in this case, for which the function is defined. So we know this is a reciprocal function that's added to a polynomial. We know that the function is defined only when this denominator is not 0, right? So f is defined when x is defined to 0. So our domain of definition will include the set of all real numbers excluding x equals to 0. So in that case, all values which are from negative infinity to the left of 0 and from 0 to positive infinity, the right of 0 to positive infinity, that's the domain of definition in interval notation. Now, after studying the domain of definition of a function, we now have to do what? Evaluate the limits at the bounds of the domain. So let's start with the limits at the bounds of the domain, df. So we'll start with negative infinity. The limit as x tends to negative infinity of f of x is equals to what? Look up. As x tends to negative infinity, this quantity dies down, right? And now this is a square term, so that this term will now become what? Positively large. So that tends to what? Positive infinity. Then the limit as x tends to 0 from the left, this bound 0 from the left, we know that the function is not defined as 0. So when you're evaluating limits at this point, we are taking values that are close to it. When it says the left of 0 means we take a value less than 0. You can take negative 0.1. When you plug it in here, you know that this function, this part of the function will be negative. Since x is very small, okay, since x is very small, getting close to 0, this quantity will be very large. Whenever you divide by a very small number, the quantity is a very large number. And now compare when you take a very small number and square it, the number becomes very, very small and positive. So it means that when you take a very large negative number, add it to a very small positive number, the answer will remain very large negatively. So it tends to what? Negative infinity. Then the limit as x tends to 0, now this bound from the right of f of x means we should take a value which is what? Greater than 0. That's the meaning. So we can take 0.1. We know again the function is not defined as 0. That's why we are taking some values which are closer to it to know how large it will be. When we take 0.1, we plug it in here, this number will become what? 2 over that small number that we've taken. And now everything will be positive in this case because x that we have chosen is positive at the bound, as we tend from 0 from the right. Now when I plug it in here, this number will become very, very large because the denominator is small, because s is small. X is tending to approaching 0 is small, so this becomes very large. And this one is also, when you square it, becomes very small. But when you take a very large number, add it to a very small number, it even becomes more larger. Okay, yes, so it tends to what? Positive infinity. So the limit, finally, the limit as x tends to positive infinity, that's the last bound of f of x. We know that the same thing here, this one will tend to what? We know that from here, this term will be 0 because when you divide by a very large number, the answer is approximately 0. So this one will just be what? infinity square, which is what a positively large number, so that tends to infinity. So having evaluated the limit at the bounds of the domain, let's look at what some other part of the function, the asymptotes. Once you have evaluated the limit at the bounds of the domain, you can deduce the equation of the asymptotes. Look up, when x was tending to 0 from the left, it tends to negative infinity. When x was tending to 0 from the right, it tends to positive infinity. So it means that what, whenever you evaluate the limit at a point, right, and it gives you either positive or negative infinity, it means that that line is what, a vertical asymptote. So my line here, x equals 0, is a vertical asymptote to my graph, and it's always usually the point where the function is not defined. Most of the times, that's how you can take it directly. Now, coming here, we see that the function is, as x tends to either positive or negative infinity, it tends to what, positive infinity. So you see, in this case, there is no, when x is getting very large, it does not approach a particular number. Okay, it does not approach a particular number. So we can see clearly that there are no horizontal asymptotes, because horizontal asymptotes are gotten, they are horizontal lines that the function approach but never touch it at infinity. Okay, so that's it. So since these values here are not real numbers, we cannot say that there is a horizontal asymptote. So it means that there is no horizontal asymptotes. Those are the asymptotes of our function. Let's go to the gradient function. So to evaluate the stationary points of a function, we need the gradient of that function. Differentiating f with respect to x, where you differentiate 1 over x, you get negative 1 on x squared multiplied by 2, we have minus 2 on x squared, differentiate 2x plus 2x. Now, this can further be written as 2 into x squared, x cubed minus 1 divided by x squared, where you add these two fractions. So after getting the gradient, you know that at the stationary point, f prime of x is equal to 0. This implies, look up, since my x cannot be 0, means that the only part that can make this expression to be 0 is what, x cubed minus 1. So it means that x cubed minus 1 is equal to 0 at the stationary point. Now from here, we recall the identity of the difference of two cubes. A cubed minus b cubed is the same as a minus b multiplied by a squared plus ab plus b squared. Now from here, we just apply it to this part. That's my a is x and my b is 1, because this can be written as 1 cube. So applying it, I'll have x minus 1 into x squared plus x plus 1, that equals to 0. From here, either x minus 1 is 0 or x squared plus x plus 1 is equal to 0. The first part is simple, s is simply 1. Then now, when you complete the square of this part, that's, we take half the coefficient of this thing, so we have x plus half the coefficient of x. Coefficient of x is 1. We take half of that, is just half. You square it. That's how you complete the square. This is just a simple trick. Now when you expand this thing, you will have a plus 1 on 4 squared. Okay, because you know we are expanding to the two terms, a binomial that is squared. You just have the first term squared plus the second term squared. So, and then 2 times a product. 2 times half will give me 1 times x will just give me this. So you see that I've introduced a certain 1 on 4, so I have to subtract minus 1 on 4 plus this one will give me 3 on 4. Clearly, this result is different to 0 for all values of x in the set of real numbers. No matter the value of x you input here in the set of real numbers, this can never be equal to 0. Okay, so it means that this part has no solution. So our only value is 1. So we have to evaluate the function value at that point. F of 1 means we come and replace x by 1, and that will give me 2 over 1 plus 1 squared, that is 3. So my point A, having coordinate 1, 3, is a stationary point. At the stationary point, f prime of x equals to 0. So let's move on to the next part of the problem. So after having evaluate the stationary points, we have to look at what the concavity of f. To get the concavity of f, we have to evaluate what the second derivative, and to differentiate the second derivative. That's to get the second derivative, we differentiate the first derivative. So using this form, the simplified form of the first derivative, we are going to have f prime of x, f double prime of x, applying the quotient rule, bottom constant x squared multiplied by the derivative of the top, which is 6x squared, minus top constant, copy all of this, multiplied by the derivative of the denominator, 2x divided by the denominator squared. Simplifying that gives me 2 into x cubed plus 2 divided by x cubed. And finally, my if I'm studying the concavity of f, I want to look at the intervals where the function is that is concave up and the region where it is concave down about a particular point. Okay, yes. So now let's look up this part. You know that when you solve this equation, okay, when you solve this equation at the point of inflection, when you solve this equation, you will have my x to be what? Negative 1.26. Let's keep that in mind. So now let's look at the when you're looking at the concavity of a function, you're looking at the boundaries where the function is increasing. I mean, that the region where it opens up and the region where it opens down. So when the function is concave up, means that the second derivative is greater than 0, which will mean that when you simplify this, okay, when you simplify this, 2 is just a constant, so the sign will depend on x cubed plus 2 divided by x cubed. So when you divide this, you have 1 plus 2 on x cubed. So I have 1 plus 2 on x cubed, which is greater than 0. And when you solve this inequality, you will be left with x less than negative 1.26, approximately to 2 decimal places. So the other case, f double prime of x is less than 0 when this same part, as we have seen, is less than 0. When you solve that, you have x to be greater than negative 1.26. So from here, we can say that the function is concave upward. Look at when f double prime of x is positive, the function is concave upward. So any value that is less than negative 1.25, that's from negative infinity to that value to the left of it, because anything less than it is to the left. So to the left of that value, the function will be concave upward in that interval. Then f will be concave downward. Sorry, here is down. F will be concave downward only when at this point from any value that is greater than negative 1.26. But remember that the line x equals to 0 is a vertical asymptote to our function. The graph cannot cross it, so it means that it will end at that point. The concavity, it will open downward at that point, okay, from negative 1.26 to the left of 0. Since it cannot cross that line, it's a vertical asymptote. We'll see that on the graph. So these are the intervals where the function is concave up and concave down respectively. Now let's look at, after studying the concavity of f, let's look at the intercept. So the point we abscissed is, you can see clearly, the point is a point of inflection. The point where on an interval where the function changes its concavity. You can see that it changes its concavity about this point. You can see the same value. So that point is always a point of inflection. Like I said, when we solve this equation, we got this point of inflection. So now let's study the intercept of the function f. So we know the function is not defined at x equals to 0, so there is no y-intercept, that is x is different to 0. No, at the y-intercept, x must be equal to 0. Since x is different to 0, according to the domain of definition of f, it means that there is no y-intercept. So for the x-intercept, the function takes a value of 0. So equating, we know that our function can also be written as 2 plus s cubed on x, where you add this 2, you can write it like this. So equate this to 0. Since the denominator cannot be 0, only this part can be 0. 2 plus s cubed. So the s cubed 2 plus s cubed will be equal to 0 if there is an x-intercept. Where you solve that, you have x to be equal to minus 1.26. From here, it means that the point, since the function takes a value of 0 at this point, so the point having coordinate minus 1.260 is the x-intercept. Now let's look at the variation table. Okay, the variation table is like what? A summary chart of everything we have done, and it's very, if you miss this table, you will miss the graph. It's just a summary, so I don't see any reason why you should fill it, but follow up how it is drawn. You have a table like this. Okay, let me show you what you fit in this table. You have the values of x in the first row. The second one will be the sign of f prime on the different intervals. And finally, the shape, the variation. That's why I call it a variation table. The variation of f on the different intervals. So let's begin by plugging in the values. We know that all the critical values that you plug in here, we have all the boundaries of the domain, and what the value of x at the turning point if there exists. So we start from negative infinity, the function was not defined. Also the asymptote, it was not defined as 0. There was a turning point at 1, and finally positive infinity. That's the span of the domain, the bounds of the domain. We insert our turning point. There was a turning point at 1 where the coordinates was 1, 3, the point A. So now finally we know that here the function takes a f prime of x. What's the sign? We studied the sign of f in the different interval. This is an interval between negative infinity and 0, and here from 0 to the right to positive infinity. First of all, we know that the function is not defined as 0, so we rule those lines. So this is what the unwanted region. This is a forbidden zone. The function is not allowed to exist in this region. It's called a forbidden zone. Okay, so here we know that f prime of x takes a value of 0 at the stationary point. That's what we said now. So at x equals to 1, it takes 0. So we put 0 there. So that's marked it out like that. From here, after doing this, we now have to write down the sign of f in the different interval. So when we are working on the interval from negative infinity to the left of 0, when you are this way, you are to the left of 0. Take any value that is less than 0 and between, that's less than 0 and also greater than negative infinity. So we can take, for instance, negative 1. We come to our gradient function f prime of x. You test it there. When you test by the sign, not the value. When you plug it in, test the sign, you end up with a negative number there. So we put negative there. So between 0 and 1, you can take 0.5. When you test in f prime of x, not f prime of x, you end up with a negative sign. And then when you take a value between 1 and positive infinity, you can test 2, for instance, it lies there, you end up with a positive value. Okay, so now that's in f prime, we are testing the values in the function, the gradient function. So those are the signs of f in a different interval. We know a function is increasing when f prime of x is positive and decreasing when f prime of x is negative on that interval. Okay, on this interval, it shows that the function is decreasing, then increasing here. So since it's decreasing, it means that it will decrease from a value that is up, not down. Okay, so I'll begin here by writing out the values of the function. This next row, I'll come here from negative infinity. What was the value as x was tending to negative infinity? It was positive infinity now. So I put positive infinity there. The function now decreases to what was here. Okay, the function cannot cross this zone. This is a forbidden zone. This part of the graph cannot cross, is a forbidden zone. So what was the value? It means that we are to the left of 0. The limit as x tends to 0 from the left was what? Negative infinity. So we put negative infinity there. Then now crossing that zone, there was another part of the function here. From 0 to the right, between this part of the function is still decreasing. It means that it will decrease from a value that is up here to something. Okay, remember there is a stationary point here. Okay, since the function even changes sign between these 2 points, it shows that it's a turning point. So the gradient changes point between about 1. So there is a turning point at that point. So now let's start from the limit as s tends to 0 from the right was equals to what? Positive infinity. Then it decreases to what? The function value at 1, which was 3. That's the minimum value. Then increase back to limit at infinity was positive infinity. So this is my variation table. So let's move on to the graph. Hope you have any question, don't hesitate to ask in the comment section. So looking at the function, I'll just copy my variation table here so that we'll use it to draw the graph without any stress. So I'll insert my coordinate axis like that. Now once you have done that, you have to plot the asymptote. There was one asymptote, the vertical asymptote. Asymptotes on graphs, on sketches of graphs, are indicated with dotted lines. So I'll indicate my x equals to 0 is a vertical line. Okay, this is my vertical asymptote. So now the first part of the function, we know we plot the critical points. There is a turning point at x equals to 1, y equals to 3. So I plotted that point there, and then the graph passes through there was an x-intercept, plot all the intercepts, only one x-intercept, negative 1.26. So this is a point here. Okay, not actually plotted to scale, but it's a sketch. It's just for you to understand. So the function, like we said, it is concave upward when x was less than this value. Okay, so it means that it will not come like this, because when it comes like this, it means that it's opening downward. So it will rather come like this, then change its concavity there. So we have the graph like that. Hope you are seeing it. So it came like that, changes its concavity at that point. Then now from that point to this zero, it was concave down, as you can see. That's the graph. It will approach this line, it will never touch it to infinity. That's why this line is called a vertical asymptote, the line that the function will approach to infinity but never touch it. Okay, then now coming here to the right, the function decreases again. Look at it, it is decreasing as you are going from this from this interval. It falls like this. Okay, it falls. So it's moving from what? From left to right. So it's decreasing. Now from the right of 0, we are here, this zone. Okay, so the function now decreases from positive infinity. It turns at this point. So you have the shape like that. It decreases from positive infinity, turns at that point, then go back to positive infinity. So that is the sketch. So hope you enjoyed the video. Don't forget to subscribe, share the video, and bye bye. See you in the next tutorial. This is Demgoon48 signing off. Bye bye.